So I stopped that last video because the way I wrote this made it really annoying when we were substituting it in. So I'm just going to try to write it in a bit of an easier way to look at, because that takes up so much space and it's just a little bit annoying. So I'm going to leave it at that now, or like that now. It should hopefully be a little bit less confusing. Alright, so this question here, we're trying to solve for t. It said calculate the time. It would take for 30% to remain. Now over in this bit and over here, we worked on the kind of info that after 50,000 years only 50% was remaining. We're working at 30% now. I'm going to write the rule down and then we can kind of manipulate that a little bit. Okay, so there's our rule. Sorry about that. Right, now it's asked us to calculate the time it would take for only 30% to remain. Alright, so that means 30% of what we started with, but we don't know exactly what we started with. But we can do this though, because 30% of what we started with is just 3 on 10 times what we started with. So if we then try to solve for t, we're going to divide by AO to start with, and that's going to give us 3 AO on 10 AO. And hopefully we can see that they'll just cancel out. So we're going to be left with this. Okay. Now we want to solve for t. So we need to make sure we rearrange this to be able to do that. So we would end up having so e to the power of 3 on 10 would be over here. No, because we're going from exponential, aren't we? Alright, so it's going to be log base e. It's a bit confusing because you've got your e and then in the power you've got your log. So there's a fair bit going on. So it's going to be log base e, 3 on 10, and that will be equal to everything that's in the power here. Times t. Alright, so to get t by itself, we could just divide this whole thing here. I'm just going to leave the negative up the top. And I'll just put this into the calculator. So if you chuck that into your CAS, you should get this. So 86,848 point yucky 848.28 years. And unlike the rabbits, you can have 0.28 years, so you can just leave it like that. That would be the answer. So it took 86,848.28 years until only 30% of the initial amount was remaining. Let's just check it to make sure that actually makes sense. So if it takes 50,000 years for 50% to remain, Does it make sense that it takes a bit longer for 30% to remain? Yes, it does. So we're all good there. If that had been something less than 50,000, hopefully you could see that that wouldn't really make sense. So let's go on to the next one. Alright, so here's another population question, but there are a couple of differences with this one as well. So we've been given a rule here, and we've been told that when the time is 2, now I don't know how long that is, does it say years? No, T months. Okay, so after 2 months we have 40,000 kangaroos there, and then after 8 months we have 45,000 kangaroos there. So looks like we're dealing with growth because we're going from 40,000 earlier to 45,000 later, and our rule here would suggest growth as well because there's no negative. Now like this one's kind of scaffolding us. If we're ever asked this question, we might not necessarily be asked to do A, but I've put that in there just to break it up a little bit so we know the steps and what we actually need to do. Alright, so we have this rule here, and we've pretty much been given 2 points. So we just want to sub both of these ones in. So when T is 2, P is 40,000, I'm going to sub it into there. So there's one, I'll call that one. And our other one over here, we're going to substitute the other info in. So when T is 8, P is 45,000. And that's all the info we really know. We haven't been told how many there were at the start. We only got told how many there were after 2 months. Okay, so it's asked us to find PO. We're going to make sure it's a whole number as it says here, and K. Now we have 2 equations up here. We have 2 unknowns, which is PO or P0 and K. So we should be able to solve for them. So this is just simultaneous equations really. What I'm looking at though is if I use elimination, I can actually get rid of PO, but only if I divide them. So if I did like 1 divided by 2, PO is going to become 1. If I do 2 divided by 1, PO is going to become 1. So it's going to get cancelled out. I might do 2 divided by 1 though, because that's going to give me a full number at the start. I'll show you. So I'm basically trying to get rid of P0 so I can solve for K. Alright, so 2 divided by 1. So that would be 45,000 divided by 40,000. Then on the other side we have that. So that was 2 divided by 1, which is there. That's supposed to be K. Alright, now over here we can work this fraction out, so you can get rid of all those zeros there. 45 divided by 40, 9 and 8, 9 fives, 8 fives. And over here you'll see those are going to cancel. So your PO and PO are going to cancel. With this bit here though, hopefully we can remember our index laws. Because it's division, you're going to have 8k minus 2k. So your answer over here is going to end up being e to the power of 6k. Alright, and we need to solve for k, don't we? So let's rearrange this. There we go, we've solved for k. Now that we have k, we should be able to find P0. I might use this one because the numbers are a little bit smaller. That might make it a little bit easier for me. go, so that's what I'm going to be doing right now. So here's my rule. Okay, so now I just want to solve for p. All I need to do is divide this on both sides to get rid of it, so it'll be p equals when I write this, I'm going to do your 2 times 1/6, which is 1/3. Okay, now what I might do is, what are we after again? We want the actual value of p and to the nearest number. So let's put this into the calculator and see what it comes up with. I did it just before, so the number that you should get, oops, 38,460. Now it did ask for the nearest whole number. If you put it in your calculator, it comes up with 38,459 point something, but we rounded up to that whole number as it told us. So here we have PO as it asked for, and here we have K. So we've answered that question. The last one for this part, we just need to use that information, or use those numbers that we worked out to find out what the population is after 4 years, as it says there. To make this easy for us, let's just write the whole rule down with all those unknowns filled in. Okay, so there's our rule. Now it's asked us to determine the kangaroo population after 4 years. If you put 4 in there, you might think you're doing the right thing, except we need to actually be smart and work out what T represents. So if you go up here, if you check, you'll see that T is actually months. So if you put 4 into here, you'd be working out how many kangaroos there are after 4 months. You don't want that. You want 4 years. So 4 years would be 48 months. So that's what we're going to put into T. There we go. Now if you put that into your calculator, what you should get is this. There we go, so 98,680.07, but again, you can't have 0.07 of a kangaroo, so therefore we're going to have 98,680. Awesome. So those questions that we were doing, they never actually told us what the growth factor was at the start. We had to work that out. With this one here, we have been told what it is. So I'll just read it. The amount of certain bacteria in a test tube is 100,000 at 10 a.m. on Monday. If the number of bacteria increases by 22% an hour, so there you go, it's told us how much it increases by rather than just showing us a K and we need to solve for it. Determine to the closest minute where when there will be 250,000 of that bacteria. So we have been working with this rule here, with the e to the power of kt, but that's only because they didn't tell us how much we're increasing by. This one, they've specifically told us that. So instead of this rule, we can use this e to the power of k is b, which is the growth rate, and the growth rate we've been told is we're increasing by 22%. Now that doesn't mean just the growth rate is 0.22, because that means you're going to be taking off, what, 78%. We want to increase by 22%. So we're always going to have 1, which is what we had initially, and then another 22%. So this is what our growth rate actually is. So do we want to find out? when there'll be 250,000 of that said bacteria. So our rule is going to be this, the amount at the start, which was 100,000, times our growth factor, which is 1.22, and to the power of t, which is how long it takes. Now it's told us that there's going to be 250,000 of that bacteria, and we want to find out the time. So this is where we put the bacteria, 250,000, and then we should be able to solve for t. So let's substitute that 250,000 in there. Okay, so we'll divide by 100,000. So that's going to be 512 over here. We want to solve for t, so we can rearrange this to a log. So t equals this, where 2 is the base. Okay, so that's the time, except that's a little bit hard for us to read. Oh, hang on, sorry, that was out of the picture. It's a little bit hard for us to read. Let's work out what that is as a decimal. So you could put that into your calculator, and it's going to give you 4.61. Now 4.61, what's the unit of measurement? Yeah, per hour. So 22% per hour. So it's going to take us 4.61 hours after 10 a.m. on Monday to get there. We want to know what that time is. So 4 hours after 10 a.m. is 2 p.m. Okay, so 4 hours after 10 a.m. is 2 p.m. So it's going to be 2 something, but we've also got 0.61 hours. We want to change that into minutes. So we want 0.61 times how many minutes there are in an hour. So 0.61 times 60, and that's going to give you 36.6 minutes. So that means it would be 230, like 6.6, except we want the closest minute. So if it's 0.6, that means we'd go up to 37. So the time would be 2:37 p.m. on Monday. There we go, done. So that one took a while, but that's one of those lessons where we just do one exercise. So have a go at these questions just there. And I might do this one in a separate video because it doesn't necessarily relate to this specific part, but that's okay. I'll show you in the next video. Okay. See ya.